All right, let's talk about doing Gauss's law for surfaces or infinite planes. Let's write that up here. Capital I. All right, Gauss's law for surfaces and infinite planes. So if this is a charged plane, we'll do the same game we did before and just say it has a charge of plus q on the whole thing. And it's infinite, right, in both directions. It's infinite in x and in y. And I want to know what the electric field is, though, at some point above the plane, at some point on the z-axis, right? So what I want to do is I'm actually going to put that on a Gaussian surface. So let's draw my Gaussian surface. I'm going to use a cylinder here because, well, it's easier to draw than a rectangle. And now for Gaussian surface, I have to say electric field times the area is equal to the charge enclosed over epsilon naught. So I have to enclose some charge for this to work. So I need my Gaussian surface to pass through the plane to enclose it. So let's go ahead and draw that. And I'll draw, so let's do like that. And then my surface will look, ooh, I should have drawn that dashed. Oh well. Kind of like that on the plane, right? So I'm going to enclose this piece of the plane. And let's draw the bottom cap too. Why not? Okay. So how do I do this? Well, I can look at the area. It doesn't matter what shape I drew. I could have drawn a rectangle or anything. I'm going to look at the area of where the electric field is passing through. Because you remember, this is actually a dot product here. So I don't care about these side areas because my electric field lines don't pass through these side areas. They're just going to go straight out the end cap on both sides, right? Because it's going to be away from the field on both sides, or away from the plane on both sides. So the sides don't matter, just the end caps. And so when I'm plugging in for this, I have to remember that I have an area up here and an area down here. So I actually have two areas. So the charge enclosed is right here, but my surface area that's going to matter, my active surface area, is really going to be 2a. So I'm going to say that your electric field is times 2a is equal to your charge enclosed over epsilon naught. And so we'll say, we'll just call this little q. So we'll just say q over epsilon naught. So now I'm just going to solve for electric field. My electric field is going to equal charge over 2 epsilon naught times your area. But once again, I don't know what this q is. But what I probably do know in this problem is I probably do know the surface charge density. And if you remember that sigma is our surface charge density, let's write that down for you guys if you want to take notes or anything. Charge density. I got space. So it is going to be actually equal to q. That's a horrible q. Q over area. Right? So I can actually just group and say that's sigma. So my electric field is then going to be q over 2. I'm sorry. Let's write this again. My electric field is going to be sigma over 2 epsilon naught. Let's put a box around that. Call it good. And just so for now that we're done with this picture, I'm going to show the electric field lines. They're going to be passing straight out of the plane, right? But they're also going to be doing it on both sides. So we'll draw it on both sides. So it's going to look kind of like that, but overall space. Let's put one more just to make it not look as oddly spaced on that side. There we go. Much better. All right. hope you guys learned something from this one, and I'll pick up in the next video with you.